All right, welcome to the part of the course where we're going to take what we've learnt about complex numbers so far and then apply them to what we've previously learnt to do with polynomials. You know, predominantly factorizing the polynomials, you're finding the zeros, solving polynomial equations. But now we're no longer going to be limited by real numbers. We're going to be, open to the potentially complex factors and solutions as well. So once you consider complex numbers as well, things actually start making a lot more sense and seem a bit more consistent. So, and this brings us to our first point that we need to know. A polynomial of degree n will always have n zeros or solutions, and also n number of linear factors. So for example, if you have a polynomial of degree 4, here we go. Let's say we've got some random polynomial here that's of degree 4. This here, if you've got complex numbers, this can be broken up into, 4 linear factors no matter what. And if we were to find the zeros of this particular equation, it will definitely have 4 solutions. Now, that wasn't always the case when you looked at these with just real numbers. And what you actually found was a polynomial of degree 4 could only have up to 4 solutions or up to 4 factors. But with the complex numbers, if it's of degree 4, it'll have 4 solutions. If it's of degree 3, it'll have 3 solutions, etc., etc. So that's the first key thing to keep in mind when we're looking at polynomials from now on. All right. We're going to mainly focus on this first video, just looking at a couple quadratics, just sort of ease ourselves into this next section. But here we have technically a polynomial of degree 2, in other words, known as a quadratic. And we're going to solve this thing for z belonging to the complex numbers. If you haven't seen this before, what this means is, z doesn't belong to the real numbers, it belongs to the complex numbers. So this symbol here, right there in the middle, this means belongs to. And then this C here, it's like a C with an extra line through it. This is just the symbol for the complex numbers, right? Just the set of all numbers that are complex. So ultimately, we're just solving the quadratic. This is all it means. We're just solving this quadratic, and z's allowed to be a complex number. That's all this really means. All right, so there's a couple different methods you could use for solving this particular equation. We're going to start off with, my personal favorite and what I'll definitely consider to be the most elegant, and that would be completing the square. So solving this particular equation, I'm going to, I've got z squared minus 6z. I'm going to complete the square. What do I need? So take the middle term, halve it and square it. We need a plus 9. So to complete the square, I need a plus 9 here. So technically what I'm going to do is I'm going to split this 13 up into a 9 plus 4, allowing us to then take these 3 terms and complete the square. So you end up with z minus 3 all squared. The positive 4 I'll take across to the other side. And, normally you'd have big issues here with us having to square root this negative number. No longer a case for us. Z minus 3 will be equal to the square root of minus 4. Therefore, taking that negative 3 across, you end up with 3 plus or minus the square root of negative 4, which, as we know, the square root of 4 is 2. The square root of minus 1 is I. So they're the solutions for it. Now, this brings us on to our second point. If we look at these 2 solutions here a little bit more carefully, let me just write them out separately, just so it becomes a little bit more obvious. If you look at the first solution and the second solution, notice that they are conjugates. 3 plus 2i and a 3 minus 2i. Now, if a polynomial, right, if we go back up to this polynomial right here, if a polynomial has real coefficients, that means the numbers in front of the z's all of those numbers there, if they're all real numbers, then any complex root will always have, the conjugate will also always be a solution. So we're not surprised here, because this polynomial had real coefficients, the 1, minus 6, and 13, any complex solution, the conjugate would have also have been a solution, which is exactly what we got when we used our completing the square method. If anyone's curious about other methods you could use, of course you could use quadratic formula. That's like, another way that would work totally fine as well. So with that being put in mind about the complex conjugates both being solutions, it kind of brings us on to the next point, which I've just written out, a little bit more formally for you, for those that are writing their notes or whatever. For polynomials with real coefficients, and this only works for real coefficients. We actually will look later on in the topic, specifically quadratics, but, polynomials that have complex coefficients, where there might be like a I in front of the x squared or something like that. This rule doesn't apply to them, right? So this idea of the complex roots always occurring in conjugates is only applicable if they're real coefficients. And there it is stated a bit more simply. All right, on to our second example. So again, we're going to solve this quadratic, and again, z's belonging to the complex numbers. So we're allowed to use, we're allowed to have complex solutions here. This one here, I've got like an odd number in the middle, and also I've got a 3 in front, so I'm super reluctant to use the completing the square method. Fortunately, we've got our quadratic formula that we can always rely on. So the way I would solve this one is I'll just go straight to the quadratic formula in this particular case. So z's going to be equal to minus b plus or minus the square root of b squared minus 4ac, so you're looking at minus 24, and it's all over 2 lots of a. So that would be a solution there. Just tidy it on up, and this ends up being a negative 23. The square root of 23 is just the square root of 23. Square root of minus 1 is an I, and it's all over 6. And if you want it written, in like, I guess the normal way we'd write it, you could split this fraction up if you wanted. You've got minus 1 on 6 as the real parts of the solutions, and then, over here you'd have the square root of 23 on 6i being the imaginary part of our two different solutions. Also noting yet again, our solutions ended up being conjugates, complex conjugates, and again this happened because if you look back at our original polynomial here, all of the coefficients, right, those numbers, were all real numbers. So again, that's applied as well. All right, on to our last example. I put this one in, although not technically a quadratic equation. I did say I was going to limit this video to just quadratics, but, it can be viewed like it's reducible to quadratic, so I thought I'd put it in anyway as sort of a fun, slightly harder type question. If you decided to replace z squared with a u, you could definitely do that and say, hey, let u equal z squared, and it would allow you to write this as just a standard quadratic equation. Going ahead, this one actually just factorizes. So what are we going to end up with along here? And then, you could then replace it back with your, well, what is u? It's actually equal to z squared. And here we go. And, if you wanted to, this is of degree 4, right? And I said at the start, you got a polynomial of degree 4. It can be split up into 4 linear factors. Let me just go ahead and do that just to show you before I then write the solutions. So the first bracket over here, the z squared minus 3, we can just use difference of two squares. So z plus the square root of 3, all times by z minus the square root of 3. And then over here, again, using that trick of like this is actually difference of two squares as well. And of course, the way you get the negative is you replace the positive with two negatives, right? But of course, that second negative is, I squared. Remember, I squared is -1. So just use that trick. And so you end up getting over here, it would be z plus root 2i and a z minus root 2i. And so that would be, you factorizing it over the complex numbers. Of course, we were just asked to solve it. So, therefore, z will be plus or minus the square root of 3 and plus or minus root 2i. So there are our examples. Hopefully that made sense. If you do need to pause and go back and re-listen to any particular parts, feel free to. If anyone was super curious about, how you would actually go ahead and factorize this expression, like if you wanted to use completing the square for all questions, you absolutely totally can. Just make sure when you do it, you want it to be monic. So, I would start off by, and again, I encourage you just to use quadratic formula here, just like we did in the official example. But if you were curious, make the quadratic monic, right? You want a 1 in front of that z squared. So I've divided everything by 3. And then from here, just use the normal approach of, I'm going to take that -2/3 over to the other side. What do you need in this spot right here to make it a perfect square? Halve the middle term and then square it. So you end up with 1/6, square that. You need to add technically 1/36 to both sides. And then, so this ends up becoming, a z plus 1/6 all squared. And it's going to be equal to, whatever this ends up being over here. Minus 23 on 2036, I think. But anyway, irrespectively, that would be your technique. Just for those that were just wondering, how would you go about using perfect square on that one? It still works, and you will still end up getting the exact same solution as we got over here. In actual fact, if you look at the scribble I've got here in the green, you can see we're almost there now. But anyway, on to the final section where you guys, I'm going to get you to have a look at these 5 questions. Pause the video, have a go at solving each of these questions. Once you've had a genuine attempt at it, unpause the video and I'll show you the solutions for the 5 questions. Alright, so hopefully you've had a chance to have a go at each of these 5 questions. The solutions, at least how I got them, and I'm not perfect, there may be a mistake with it, but these were the solutions I got. So hopefully you found the video useful. In the next part of the videos, the next video I'll produce, it'll continue what we've done, but again, we're going to look at polynomials of higher powers and, just getting a reminder of how the remainder theorem works and how we can apply that as well with our complex numbers. All right, hopefully this has helped, and I'll see you in the next one. Bye.